we're kind of going over different ways of looking at radiation, looking at molecules that are changing state from one nuclear state to another one, and kind of seeing how does that affect things. And we talked about two different particle types that could occur with, which were these alpha particles, and they've got a little symbol that has this little kind of alpha shape that kind of looks like a little fish almost. First letter imagery alphabet there. Sometimes older books, you'll just see it written as the letter HE as well. Two different ways of noting the same thing. And these are both being particles being emitted, so these are matter that's being released there. So in either case, we're releasing some matter, but we're releasing matter in the form of a couple of different particles. We're changing one nucleus to another. And we're changing one nucleus from an unstable nucleus, a nucleus that doesn't have quite the right amount of protons or the quite the right amount of neutrons, to something that has a more stable, proper ratio between protons and neutrons, and hopefully that'll prevent it from decaying any further, right? You're basically changing one atom to another type, and you can do that in a couple of different ways, and that's what we're kind of finishing up with last time, talking about some of the different ways that a particle or an atom can change from one type of atom into another type of atom, and this is done to stabilize that atom by releasing some matter. And one of the matters they could release is basically just a small alpha particle or a small helium piece of atom. So you have one big atom, and you're basically going to break off a small piece of it, and that piece is going to come off, and then you'll have the rest of the atom missing that little part that would have been there. So we're going to break off a small part of that atom, and we're breaking off 2 protons and 2 neutrons. So our mass is going to go down by quite a bit. We're going to lose 2 protons from that atom. We're going to lose 2 neutrons from that atom. Since mass numbers are just the number of protons and the number of neutrons, we're going to go down by a mass of 4. We're going to lose 2 protons, 2 neutrons for that. But that also means our atomic number is going to go down because we're going to lose 2 protons. The atomic number is the number of protons there. So if we lose 1 proton, our atomic number goes down by 1. We're losing 2. So we're going to change elements. We're going to be 2 lower. So if we started with something like 92, we're going to go down to 90. We're going to change our atomic number. Mass is going to go down as well. And that's going to, by changing that ratio there, by losing some protons, losing some neutrons, hopefully it becomes more stable. Maybe does, maybe doesn't. Maybe another reaction happens afterwards and it does this again. But you're changing one element type into another type, and we'll see that as one of the kind of nuclear decay processes. That's one way of doing this. But there are other ways as well. So there's other ways of changing your atoms as well. You could change matter from one type to another type by also releasing these beta particles. And these are, it's a big letter B with a little tail. And the other important part about this is it does have this little minus on it afterwards. And that's letting us know that these are betas that have a negative charge to them. So just like alphas have a positive charge, like protons are +1, we got 2 protons, so we actually have a +2 charge overall on this thing. This one's got a -1 charge when it comes off. So it's releasing something with a -1 charge. That -1 charge is being released there, and that -1 charge particle there is going to change our atomic number as well. But for betas, you're actually changing your atomic number by going up. So your atomic number is going to increase, so the number of protons goes up, and the number of neutrons goes down. So proton number goes up by 1, neutron number goes down by 1. Overall net change 0 of the mass, right? If you lose 1 proton but gain a neutron, or lose a neutron but gain a proton, the overall number of protons and neutrons together doesn't change. So the total mass stays the same. It's just the number of protons and neutrons is going to shift around a little bit. But we're going to overall increase our atomic number by 1. Our proton number is going to go up. But then we're going to lose a neutron so that we don't see an overall change of the mass. But this is also going to change one element into another type. It's going to change one element from one number to one higher up. So you go from 16 to 17, or 19 to 20, or 33 to 34. Your atomic number is going to go up by 1. And then the atomic number is going to go up, but the mass doesn't change. So whatever the mass happened to be, the total number of protons and neutrons, that doesn't change. That number doesn't change. It stays the same, but the mass number goes to the same, but the atomic number is going to go up. And that's important to remember, too, that there's this little minus here, and that's going to help us when we're trying to settle out and sort out the symbols for these different things. If you look at beta equations here, like this one here, right? The mass doesn't change. The overall mass on top, the 19 for these stays the same, right? 19 to start, on the left. And the final product element also has a 19, but the atomic number went from 8 to 9. And one way to remember that is that that little minus there also lets you know to put a -1 down here to remind you that your atomic number is going to go up. But just so that everything kind of cancels out, atomic number went from 8 to 9, it went up by 1. We're going to put a little -1 right there. So that 8 and 9 come up together to the same number. 8 is the same as 9 minus 1. So we'll see that happen there. But again, our atomic number is going to go up, but our mass is going to stay the same. And those are kind of the two different things we talked about last time, two different ways of kind of changing our atomic numbers, changing atoms from one type to another with different kind of nuclear changes there. And betas are one of the sources there. And again, we've always been putting this little minus there because there's also kind of an opposite beta, which is called a positron. And now this beta has a little plus after it. So positrons are betas that are positive. So it's very similar to that beta emission. But the difference is rather than making the atomic number go up with beta, positron is going to make our atomic numbers go down. So the mass is still going to stay the same. Just like before, we started with 18. We're going to end with 18, but we're releasing we're going down an atomic number now. So we got kind of beta versus positron. Just to jump to this little thing here, right? So positrons have this little plus there because our atomic number is going to go up, down, versus our betas, the atomic number is going to go up. So here, atomic number is going up, and here the atomic number is going down. And those are the two different ways of kind of changing atomic numbers without changing your mass. So in both cases, the mass stays the same, but it's just you're turning a proton into a neutron, or turning a neutron into a proton. You're kind of switching around the composition of that atom. You're going to change its atomic nature because you're changing its number of protons either up or down. So you are turning one element into another type of element, but you're going to keep the mass the same. You're not going to go up or down in mass for those cases there. And this is just kind of showing an example of a mass. You see either case, these masses are staying the same. Again, you see that little beta symbol for both of them, the little b there. But B minus is the beta, so we have a minus here to let us know our atomic number is going to go up, versus over here, a B plus is letting us know our atomic number is going down. So we got those two different ways of kind of changing atomic numbers, changing our atomic numbers, but keeping our mass the same. So if you see a nuclear reaction and you see the mass at the beginning and the mass at the end not change, and that's what we see for all these cases, actually. We see the mass is the same, so we know it's not alpha, because alpha, the mass is going to go down by 4. Mass is going to go down with alpha, but with beta and positron, it's going to stay the same. So we can rule out one of our types of decays just by looking at mass. But then when you have the mass changing, or not changing, you have to then kind of look at the atomic number. Again, for an alpha, the atomic number is going to go down by 2. For a beta, the atomic number actually goes up. And then for the positron, the atomic number goes down, but by only 1. So if you see a 2 drop, then you know it's probably alpha. If you see a 1 drop in atomic number, it's more of a beta, a positron type reaction there. But again, we can see that the total masses aren't changing for any of these. It's just changing that atomic number, either going up or down, depending on which reaction that you have there. But these are all different types of particles that are going to change our atoms from one sort of atom into another sort of atom, right? We're changing nitrogens into carbons over here, or changing nitrogens into oxygens. So one type of atom could actually undergo multiple different types of decays, but we'd have to tell you which one it is. So here we're saying that nitrogen is doing a positron turning into carbon. Here we're saying nitrogen does a beta turning into oxygen. Different types of reactions are going to turn those atoms into different types of elements, depending on what type of decay we work with. So we're always going to tell you what it is. So we'll always let you know what type of reaction it is or what type of decay to look for. So whether it's going to be nitrogen with beta or nitrogen with carbon, we'll let you know what the type of reaction is, but it is going to change one element to another type there. So that was kind of, so those are the 3 different types of particles or the different types of matter. So we talked about 3 different types of matter. We have the alpha matter, the beta, and then the positron, same symbol for those. So those are all different types of matter that an element could give off. Matters have mass, matters have volume. They're made of different types of particles. And these are ways that elements are going to try to become more stable by kicking off these little bits of matter. And that's the 3 decay types that you're going to see for those. But there is a fourth way of kind of stabilizing an element as well, and to make an element give off some stability, become more stable. But this one uses energy instead. So this is rather than using matter like the alphas and the betas. So right, so alpha, beta, positron, these are all matter. And then gammas are energy. So we could also give off energy. So matter, universe is made of 2 things, matter and energy. Gammas are a type of energy. Gammas essentially are a type of light. So very high energy X-ray. X-rays are a form of light, very high energy light being released. So intense that it's in the X-ray, gamma ray region of the spectrum. So these nucleuses have just too much energy, and they could give off that energy by kind of kicking off some matter, get some stability there. But they could also kick off energy too. So it's just like if you're having a really stressful day and you need to kind of get out some stress, you could go for a run, you could go for play some loud music, you could shout, you could do something to kind of get that energy out. That's what these atoms are doing too. These atoms are releasing energy by giving off some energy, but atoms have so much energy inside them that rather than just giving off sound energy if you're shouting, an atom gives off energy in the light spectra, and it's giving off light, but it's so bright and so intense that we actually can't see it. It's in the X-ray band there. So very high energy being released, but energy is not matter. So energy is not matter. The mass isn't going to change of this nucleus because we're not working with matter. We're working with energy. And if we're not working with matter, we're working with energy. We're not going to change the atomic number. We're not going to change the mass number. And it's not really going to look any different. The atom's going to look the same, but it's going to have a lower amount of energy. So there's kind of different ways of noting that. Sometimes they put a little star on one side to say that, hey, this atom's got too much energy. And then when it gets off, when it gives off that gamma, then there's no star afterwards. So sometimes they'll write kind of little notes like that. But gammas also can hang out with the other reagent decay types as well. So you could have an atom that's giving off both alpha particles and gamma rays, or beta and gamma, or positron and gamma. So the gamma could be released alongside those particles, or it could be given off on its own. And we'll let you know either way what's going on there. But these are the radiations that people are worried about. So when people are worried about radiation, when they see the little radiation logo, like that, usually they're not too worried about alpha particles. Alpha particles are, in terms of mass, are pretty large. They got a mass of 4. These betas are pretty small. But even for the betas that are kind of the mass of an electron, they can't go very far on their own. If you get kicking off of an atom, kicking off some alpha rays, kicking off some beta particles, you could block those probably with this chalkboard or even a couple pieces of aluminum foil. We did this in lab a little bit, trying to block the different sources. Alphas and betas are relatively easy to stop. But gammas are really, really hard. And gammas are the one that people worry about because it is so hard to stop a gamma. You need a lot of concrete or a lot of lead. So when people are worried about radiation, this is the radiation they're really worried about. They're worried about these gamma radiation sources more so than the other ones. So those are kind of the things people worry about a little bit more. So when we're working with kind of these gammas, right? So gammas have a lot of energy. And to kind of put that energy into perspective, there's all sorts of other light that can be released as well. And some light has lots of energy and some light has relatively low energy. So radio waves coming off your cell phone, microwaves coming out of the little machine you use to heat up your water, those are relatively low energy. And part of the reason that light has kind of different intensities of energy, you can kind of think of it as little waves. So if you go to the beach and it's a pretty calm day, you could stand up in the water, you get hit by a few waves, no big deal. Maybe even if there's a really big storm, you get a nice 8-foot high wave, it might knock you over, but you have plenty of time to stand up before the next wave comes and knocks you over again. But if it's really, really stormy and a wave hits you over and you try to stand up and another wave hits you again, you're going to have a hard time. And that's what happens with these lights. Some light has really long wavelengths, doesn't hit you very often. 1 radio wave every second, 2 radio waves every second, you're not going to feel anything. But if you get hit by thousands of waves per second, like with the gamma and the X-rays, you're going to start to have a problem. And that's why the radiation in the gamma X-ray is able to go through things. It can go through your skin, it can go through your bones, and you can see X-rays of different kind of regions of your body. So if you're trying to look for breaks in bones, you hit them with X-rays, you put film on the other side, and you see if there's any holes in the bone. You can actually look for that by using really high intensity energy. We can look for fractures and other issues there. But we can also use these to detect things, right? If somebody's trying to hide something or smuggle something through, we use X-ray machines at airports because it goes right through the bag and it can see the different things. It sees everything except the things that absorb X-rays and gamma rays. So only really dense matter, things like heavy metals, other materials like that that can absorb gamma and X-rays are going to be visible. And then gamma rays are even harder to block. So if you're having a hard time seeing something with X-ray vision, you could switch over to a gamma vision and try to see through things that even the X-rays can't get through. So they're very high intensity light, but that also means that if we're getting hit by these, we're getting hit by all that energy. So we're going to try to avoid that exposure to the X-rays and the gamma rays because it can cause some problems as well for us. So we'll talk about in a couple of seconds how what happens if you get hit by too many of these different things. But even ultraviolet UV light has some problems, right? If you go outside for a long time, they want you to put on sunscreen to block the UV light from getting to your skin, causing skin cancer. If you stare at the sun too long, you can damage your eyes from UV light. So UV light already is pretty intense, pretty damaging. The X-rays and the gamma rays are even more dangerous than that, to put that into perspective. But lucky for us, we don't see these very often, so we don't have to worry as much. UV light we see every day. X-rays and gamma rays are a little bit rarer, hopefully, in your life. But if you are working with those, you want to kind of avoid that exposure. So we kind of talked about all these different types of decays again. We got 3 that are made of matter. So 3 matter types right here. And then 1 energy type. So that's that. So again, if you're looking at these, you can almost tell what kind of reaction's going on by just looking at what happens, right? Does the mass change, yes or no? Well, if the mass goes down, then you know it's alpha. If the mass doesn't go down, it's one of the other 3. So you can't tell from just mass alone. But you could look at what happens to the atomic number, and that actually would tell you, does the mass go down? Does the mass go up? Does the mass go down by 1? Or does the mass change at all? These will all kind of tell you. So the change in atomic number is usually the easiest way to see what's going on, but you could also look at mass changes. You could look at energy changes, things like that. And this was just kind of writing kind of showing some examples from there. So being able to kind of read and write these equations, being able to understand what's going on. So like for this one here, it was talking about bromine, and it's talking about bromine with a mass of 84. So we could go to our periodic table. They're telling us bromine is the Br element right there. So if we're going to look at this element right here, right, we got bromine. So we'll write the symbol for bromine. And they gave us a mass right here. So this is our mass, 84. So mass of bromine, 84. Periodic table, this one's not the best one, but it does have the atomic number. Atomic number is the number of protons right there. So if we're going to write that out, we can put that down here to keep track of it. So bromine had 35 protons, and it had 35 minus 84, so something 39 neutrons, right? So 60, 70, 49, there you go, yep. So 49. So if we had that kind of element right there, so that was kind of our starting element. But what happens is we're going to give off a beta. And in beta, if we go back, we can go back to our little cheat sheet right here. Atomic number is going to go up by 1, but the mass is going to stay the same. So for our beta there, our atomic number is going to go up versus positron, the atomic number is going to go down. So looking at this element right here, right, we know our beta is going to go on. So our atomic number is going to go up. So that means our proton number is going to go up. We're going to go from 35 to 36. So let's put that there, and we could actually write it over here too. So now we got 36 protons, which means we only have 48 neutrons. So we've kind of changed our proton-neutron ratio right there. We went from having 35 and 49 to having 36 and 48. And hopefully after that happens, the element's going to be a little bit more stable and not radioactive anymore. But we can write out everything else too, right? So we have the mass doesn't change when you work with betas, so we can leave that mass the same, this 84 right here. And then our atomic number went from 35 to 36, and went up by 1. And we could check actually what element we're working with, right? We're working with bromine. So bromine's atomic number is going to go up. It's going to go from 35 to 36. Our bromine's going to turn into a krypton, a Kr. So we're changing elements there, but we also got to write everything else out, right? This equation right now is just showing that we spontaneously gained a proton or converted a proton. So we should write the other thing that happened there so people know why that happened. And it's because we had that beta particle being released. So that beta particle is being released. And then the symbol for the betas, right, those are the negative ones. And usually they also put a 0 here and a -1 here. And this is basically letting you know that your atomic number changed. Your atomic number went from 35 protons to 36 protons. That happened by a nuclear change inside the nucleus. But then 36 minus 1 still equal to 35. So everything still balances out because 36 and -1 comes to 35. So that's kind of stabilizing that out. So this is the equation. If you're going to write the nuclear equation for a reaction that involved bromine, in this case, bromine giving off a beta. So they have to tell you that. We wouldn't expect you to know that on your own, but maybe instead we gave you the equation written like that. You'd have to fill it in that way. Or maybe they want to put in this part. A couple different ways they could write or explain that, but showing that something happened. And then positron's kind of the opposite of this. So if we had a positron type reaction going on here, we know that positrons look really similar. They still have a mass of 0, but they have the +1. So whatever is going to go on with this oxygen reaction, rather than having a 0 and a -1 there, the positron is going to be the one with the +1. So we could do the same thing, though. We know something with a mass of 15. Oxygen right here is 8. So we've got oxygen being changed here. And again, if we had beta decay, our atomic number would go up. Versus if we had positron, our atomic number is going to go down in this case, right? Positrons' atomic numbers go down. And we can check that on the previous page if we need to. Let's go back to, oh my God. So positrons, right? Positrons' atomic numbers go down by 1 while the mass stays the same. So if our atomic number is going down by 1, mass is going to stay the same. So our atomic number is going to change, but our mass doesn't. So whatever we're going to have, it's still going to have a mass of 15. And that makes sense. Oops. Make that an arrow. That makes sense, though, because, right, because just like over here, mass doesn't change. Over here, the mass doesn't change. So still got a mass of 15 on this side, mass of 15 on this side. But we need our atomic number to go down. We're going to go from 8 to 7. When we go from 8 protons to 7 protons, our symbol changes from the letter O to the letter N. And then we can put the little 7 down here to help people keep track of that. But 7 plus 1 is the same as 8. So we're seeing that same thing happening again and again. So that's kind of an example, again, 2 of these different decay equations. Maybe they give you one, maybe they ask for one, or some different ways of looking at that. But you can look at the periodic table, right? This bromine, so this is the beta would give us, so if we started with bromine right here, if we did beta, which is the B minus, versus positron, which was the B plus, versus if we did alpha, right, we would have gone, our atomic number would have gone down by 2. We would have gone all the way down to this AS sample right here. So we can change from bromine into 3 different types of elements depending on what type of decay they tell you is going on. So you have a couple different options. So we just always got to check what they tell us happened, what kind of mass change we may go to, what particles we're giving off there. But there's a few different options that could happen for all these different elements, depending on whether it's alpha or beta or positron, or even if it was gamma. If it was gamma, it may stay the same. It just may be going from a higher energy to a lower energy type of reaction there. So lots of different decay types, again, that can happen depending on what element you're working with. Just like we see here, different types of things. Some change our atomic number, or all of them change our atomic number except for 1, but it could go up by 1, down by 1, down by 2. Mass may or may not change as well for those different types of decays. I'm going to skip that one. And this one I liked. So this one's a nice little one because we can kind of look at it on the board too. But right, so this is kind of just showing mercury changing by a positron, but they actually give us 4 different versions of the answer right there, because one of them has more of a gamma type decay. One of them has more of a positron type decay. One of them's more alpha-like. So you can see, but for all of these, right, we could check, do these make sense in terms of what they're written? Maybe one of these is written the wrong way in terms of mass, but actually it turns out, right, 188 to start with, 188 to end with. 80 and 81 and -1, so that one balances. 188 to start, 188 to end. That balances as well because 80 to 80. So this is showing a gamma. Maybe this has a little star after it to let us know it was high energy to low energy. But these are all different types of, oops, add more time while we talk about this. So while we kind of talk this through some more, but right, all of these look like they're actually balanced, right? 188 minus 4 goes to 184. 80 minus 2, 78. So one of the things you could do is just check. Maybe some of these are written wrong. The masses don't balance out. Unfortunately for this, they all did balance out properly. So these are all proper equations, but one of them is describing something a little more like the alpha. One of them is describing a little bit more. Move that another 20 seconds while we talk about the other ones. Right, so this first one here is a little bit more like alpha type decay, right? The alpha decay, the symbol for the alpha. So if you remembered the symbols, that may be one way to look for this. So that's alpha. Maybe you don't remember what the symbol for alpha looks like, but you remember that alpha is the one where the mass goes down by 4. So you look for that instead. But either way, you'll probably be able to rule that one out. And then gammas also, maybe you remember that gammas don't change anything, so you could rule that one out too. But then you're left with C and D, and you're like, okay, I remember beta and positron both have that symbol that looks like that little B. So it's one of these two, but then you could kind of remember or try to think about, is it beta minus versus beta plus? The minus is the beta, the plus is the positron. Maybe you remember that way. Positrons are positive, pluses are positive as well. Maybe that's how you remember that was the positron. Maybe instead you remember that positrons are the one that make the atomic number go down. So going from 80 to 79, that could help you as well. So a couple different ways to remember that and to kind of work out this problem. But let's see how everybody did. So yep, most people went with B, so they were right. So a lot of people went with that answer there. So kind of answering it right, that yeah, this is the one that has a positron, it's positively charged. But that's kind of an example of maybe a question if it was more multiple choice written. If not, maybe they just ask you to write out the equation instead, then you'd have to write it on your own. But that's not as easy for like a little survey type thing like that. So that was good. So people did good for that. So when we're working with these reactions, nuclear decays, right, we talked about different types of particles and different types of emissions. And we'll talk about kind of what happens when you get hit by these things as well, probably today. But the other thing to talk about kind of for a little bit of time is that how often this happens. And these actually happen at a pretty understandable, pretty predictable rate. So if you have a particle that's radioactive or a thing that's radioactive, it's going to give off radiation at a fairly predictable rate. And you actually can predict that rate using kind of different observations and kind of figuring it out. So every material breaks down at its own rate. Some things break down really, really slow. Other things break down really, really fast. And it kind of varies with the item to the item. So something like that oxygen we talked about before, it only lasts about a pretty short time compared to something like the uranium, which lasts significantly longer. So some radioactive materials exist for really long amounts of time. Other things exist for relatively short times. And you can't really predict it based on anything. There's no way to guess this, but there's plenty of studies that let us know what they are. So everything has its own kind of breakdown rate. But what they do is they measure this in terms of what's called a half-life. If you had a big block of radioactive material, after one half-life of that material, half the material would be gone. So if you started with 1,000 grams of radioactive oxygen, after one half-life, you'd only have 500 left. The other 500 would have turned into something else. It would have broken down into fluorine or bromine or whatever the radioactive byproduct of that oxygen is. So for our oxygen here, that means after 2 minutes, we lost all of that stuff. But we still have the other 500 grams, the other 50% still there. But if we waited another 2 minutes, that would go away as well. So now it's been 4 minutes total, 2 minutes plus another 2 minutes for there. And that's going to just keep happening for all these different radioactive particles. So if we wait another 2 minutes, we'll go to 6 minutes total. 2 minutes plus 2 minutes plus 2 minutes, half of that's going to go away. So you can see it takes a little while before everything goes away, because we're going to just keep doing this. It's that game where you keep making smaller and smaller pieces. So now it's been 8 minutes. Now it's been 10 minutes. And then, we're going to keep doing that 12. So it's going to take a while to get down to nothing. But every time your big block gets cut in half, and then that block gets cut in half. So if you had a half-life of 2 minutes, it'll take a while, but 2 times 10 is 20 minutes. Versus if you had a half-life of 1,000 years, 10 times 1,000 years is 10,000 years. So for some of these elements, even breaking down half of the material takes a really long time. Versus for other elements that last for only seconds, breaking down half or 10 halves of material is relatively quick. So different elements break down at kind of different rates, but you can kind of see how this is going to take a while. Even if it has a pretty short half-life, it may take a while. So if you had 128 atoms, after one half-life, you're going to have 50% of the atoms gone, 50% of the atoms left. So you'd go from 128 down to 64. If you had 2 half-lives happen, you're going to go from 64 to 32. You're only going to have 25% of that sample left. So after 2 half-lives, you're going to go down by a factor of 4. 4 half-lives, we're going to go from 128 to 64 to 32 to 16 to 8. And it just keeps going every time. Eventually, you'll get down to 4. Eventually, you'll get down to 2. Eventually, get down to 1. And then after that half-life, it's either going to be half an atom left, which you can't have. So it's either going to stick around or it's not. So you'll either have 1 or none, depending on what the kind of half-life is. But after about 10 half-lives, you can safely say that pretty much all the atoms are going to be gone. But it's this kind of slow process. It takes a really long time to lose those atoms. And if your atom has a really long half-life, right? If this was a half-life of 1 hour, it would take 7 hours to get to here. But if this was a half-life of 1 year, it would take 7 years. Or if the half-life was 1 million years, 7 million years. So really short half-life elements, they go away pretty quick. But long half-life radioactive materials, they take a really long time. Because even 2 half-lives to get down to a quarter may take centuries or millennia to happen. And this is just kind of showing some different radioactive materials again from that page. Some materials list a really long time. It takes 4 billion years for half of your uranium to decay. But it only takes 28 years for half your strontium to decay. So in the time that 1 uranium goes away, all the strontium's going to be gone. Or in the time that 1 strontium's gone, all the oxygen's going to be gone. Some elements break down really, really, really quickly. So if you had some radioactive oxygen, you're going to need to work really fast because it's going to go away pretty quick. Versus if you're working with this iodide, you can take your time. It's not going to go away at a really noticeable rate. And we use these for different types of medicine. We use these for diagnostic tests to look for people who have, maybe if we're worried somebody has a tumor or somebody has some type of other disease, we can actually use these to detect those. So oxygen, if you're worried about somebody's oxygen level, basically how well do their lungs work, how well does their heart work, right? We got to carry oxygen around to breathe. Well, rather than giving them normal oxygen, which is fine to breathe in, you could also make some radioactive oxygen. Radioactive oxygen behaves the same as regular oxygen. It's safe to breathe in. It's got a little bit of radiation coming off of it. Again, it's only going to be radioactive for a very short amount of time. But radioactive oxygen can go through your bloodstream, can travel up to your brain, no problem. Your brain absorbs it, gets the energy oxygen it needs to conduct its reactions. You breathe it out as CO2. But if you think somebody's maybe got a little block in one of their blood vessels, you would see the oxygen go into their lungs, and it makes its way and it stops, and it doesn't get onto the fingertips or it doesn't get up to the brain. You can actually use this to look for strokes in people. So we can use radioactive material to look for things. Otherwise, right, how would you look for strokes in a blood vessel? You'd have to actually send a little camera or something through their blood. And that takes a lot longer to do than just to look for where the radiation goes. So these can be very non-invasive ways of looking for issues with blood flow, issues with cancer, potential tumors, looking for breaks and fractures. We can use radiation as long as we know what we're working with and as long as we're really careful with what we're working with to actually look for diagnostic tests without having to cut somebody open or do any kind of more invasive surgeries, at least as a screen. Maybe then you have to go and do something later. But if you're just worried about, let's test this before we cut your veins open, we can do that. So we can use these But some materials only going to exist for a short amount of time, get to work quick. Other materials maybe exist a little bit longer. So we can kind of see examples of that. And if we were working with radioactive stuff, we can use those half-lives to figure out how much stuff we have left. So if we wanted to give somebody some oxygen, right, how much time do we have before the oxygen's all gone? If we need a certain amount of oxygen or a certain amount of radiation, right, how many minutes is it going to take to get to that room? How many minutes is it going to take to hook somebody up to the machine? Is it all going to be gone before they even get to the machine, or is it going to be adjusted time-wise? You can figure that out, so that can help you kind of plan your treatment courses, plan your experiments with people. So we could do an example, right? So like this is an example here. Iodine's a nice little sample. This is used for people who are worried about thyroid cancer. Iodine's a good sample for that, to look for things. And iodine's got a relatively good half-life in terms of hospital times, right? 2 hours gives you enough time to kind of hook somebody up, have somebody ingest something, gives it time to go through the body, has it time before it starts to get decay too much. So if you were worried about somebody having thyroid cancer or wanted to do a thyroid screen, one of the things they may have you do is ingest some radioactive iodine, iodine-132. So we don't have to, they didn't ask for this question, but we could do it anyway. So this is iodine-132. So if somebody were to ingest some of this iodine, it would go into their bloodstream, it would go throughout their body. Your thyroid has a good amount of iodine in it. And if you have a thyroid cancer, it really, really snatches up all the iodine out of your blood. So if somebody had thyroid cancer, it would snatch up all this iodine right away and actually start to accumulate there where you could detect it. If you didn't have thyroid cancer, it's going to just hang out in the bloodstream, kind of go through its way. So you'd see kind of low level of radiation everywhere. Versus if somebody has thyroid cancer, it's going to be kind of accumulating in one spot. So this is a check for that without having to do anything else invasive. But we got this iodine right here, and they're telling us it gives off betas. So betas are 0, -1 with a little b minus symbol here. And they also told it broke down into xenon gas. So that's just going to be Xe. It's iodine-132. Beta's masses don't change. So we don't need to write the nuclear equation there, but it never hurts to have it, just to kind of help keep track of stuff. So this is what we're working with. We're working with this iodine atom. It's going to break down by giving off some beta particles that are radioactive. And those particles can be detected with special detectors, so that we'll actually figure out where this iodine goes. And then it's also going to turn into this little gas. And they're saying that we had 100 milligrams of this sample initially. So we have 100 milligrams, that's just a mass unit. And initially there's going to be none of this stuff because there's no radiation yet. But eventually this 100 is going to break down and it's going to turn into that other element as well. And they told us the half-life. They told us the half-life of this is 2.3 hours. So after 2.3 hours, we won't have 100 anymore. We're only going to have half of that. And after even more time, we're going to have less and less and less. So we could kind of look at, oh, we did have an equation there. Cool. So let's clear that. Yep. So we're turning iodine into xenon right there. So same thing we just did ourselves, but we can look at it with the nice writing instead. So we got our iodine turning from one thing to another. And then we want to figure out what we started with, right? So we started with one, so at one half-life, this has been 2.3 hours. So we started at 0. So 0 hours right here. We were at 100. 2.3 hours later, we only have 50 left. So we went from having 100% iodine to 50% iodine, 50% xenon. And if we let another half-life happen, it's going to break down even more. 2.3 hours later, we're going to start with 50, but we're going to go from 50 down to 25. So our sample now has gone even more from iodine to xenon. Now we got 3 times as much one as we did the other. And if we let it go a third time, it's going to go from 25 down to 12. Because right, this was 0, 2.3 hours. From at the start of 2.3 hours, we're at 50. But then 2.3 times 2 is 4.6. So we went from 0 to 2.3. That was the first half-life. That took us from 100 to 50. And then from 50 down to 25 with another 2.3. So that's 4.6. And if we do it one more time, 2.3 plus 2.3 is 6.9. So we would go from 0 to 50 in the first 2.3 hours, 50 to 25 in the second 2.3, so 2.3 times 2, 4.6. And then one more time from 25 to 12 with 6.9 there. So we're seeing every time it goes smaller and smaller and smaller. And they wanted to know how long does it take to get to this mass here. So we basically just take our 100 and keep dividing by 2. So 100 divided by 2, and then divide that number by 2. And you basically keep dividing by 2 until you get down to 12.5, which is what we did here. We divided 100 by 2 once, so we got 50. Divided 50 by 2, got 25. 25 divided by 2 gives us 12.5. So we just kept dividing by 2 until we got to the mass that they were looking for. Mass they were looking for was the 12.5. And then we just figure out how many half-lives had to do that. We had to go 1, 2, 3 half-life times. 3 times 2.9 or 2.3. So that gives us kind of a 6.9 time frame there. So 1 half-life was 2.3, sorry, 2.3 times 1. Versus 2 half-lives, 2.3 times 2, versus 3 half-lives, 2.3 times 3. Right, so depending on how many half-lives you have, you just multiply the half-lives by how long the half-life was. So we could do this for any problem, right? If they instead said the half-life was 1 hour, it would just be the half-life times 3, or 1. If the half-life was 100 years, the half-life 100 years times the 3 there. So whatever number of half-lives happen, we just multiply that number again at the end. And that tells us how long it actually was versus how many half-lives times it was, right? If there were 3 half-lives and each half-life is a certain amount of time, we can kind of figure that out. But for these types of problems, we're always going to give you standard numbers of half-lives. 1, 2, 3. It's never going to be 2.5 or 1.5. It'll always be a whole number. Makes it a little bit easier. So all you have to do is divide by 2 each time rather than using the other half-life equations from math. Dividing by 2 is a lot easier to do than the exponential form there. But you can kind of basically figure out, right, how much of anything is left over at a certain amount of time. As long as you know what you started with and what you ended with and how long it takes to go down by half, we can figure out how many times do we have to divide this by 2 to get to the right amount. And whether they tell you the starting and the ending masses, or maybe they tell you the starting and the ending times, and they want you to figure out the mass. As long as you know one of those 2 things, you can figure out the other one. So just like here, whoops, I'll go back. So just like here, this is kind of like a multiple choice type question again, but it's talking about another element. So TC, so let's put the 99 there. They didn't tell it what it turned into, but we know it's giving off some kind of radioactive decay. This is our radioactive material here. So they're telling us that at a certain time, we had a certain amount. So it's saying here they were given 25 grams. So that sounds like a starting amount, 25 grams. And do they tell us what time? They tell us at the time. So 6 a.m. So we can write that down too. So we're just kind of writing down all the information we have. So at 6 a.m., we have 25 grams of this particular material. And they want to know, basically, in this case, how much remains. So they're not sure what the final question is. So you had some amount, you started with 25, and you're going to end with question mark. We don't know how much we have at the end, but we know it is going to break down over time, and it has a certain rate at which it breaks down. So our half-life here is 6 hours. So if we started at 6 a.m., right, we started at 6 a.m. where you had 25, so they took 25 of the stuff, they put it in somebody, they're going to do a procedure, maybe they're going to look for a heart blockage, maybe let's go to a brain scan, whatever they're going to do. At the end of the day, you have to figure out, is it safe for this person to go home? They have to have they can only have a certain amount left in them before you let them get in the car and head out of the hospital. So they want to know, all right, is 6 o'clock late enough, or do we have to wait longer? So 6 hours after 6 a.m., so 6 a.m. plus 6 hours, this is 1 half-life. So let's call it 1 right here. So that's our first half-life, 6 hours later than 6. So if we started at 6 a.m., 6 a.m. plus 6 hours, that's going to be basically noon, 12 o'clock. So we got 12 noon here. And what happens is 1 half-life happened. So we started with 25. We're going to divide that by 2. Yeah, and we're going to go from 25 to 12 and a half. So If you want to know, so at noon, this person says, hey, how much stuff do I have left in them? You could say, all right, it's noon, it's been about 6 hours, it's been one half-life. You went from 25 to 12 and a half. But hospital rules say you can't go home until you're below 8. So sorry, you're at 12, 12's above 8, you gotta wait here longer. And they say, all right, fine, I'll wait around. So 6 hours later from 12 noon, 6 hours later is 6 p.m. So now it's almost dinner time. They're saying, hey, I'm hungry. Can I go home yet? Let's figure out how much you have left in you. You're probably gonna use a detector or something too, but just based on math, we could also say that, well, it's been 12 and a half, 6 hours. It's been a second half-life. So it's been another half-life there. So it's been 6 hours plus 6 hours, right? 6 a.m. to 1, 2, 6 p.m. Again, one half-life has passed. So 12 and a half, we can divide that by 2. And it goes down to, 6.25 grams. And again, right, the hospital says you have to be under 8. 6 is under 8. So they say, hey, can I go home? I'm hungry. And you can say, yes, you can go home because you're less than 8 for that rule. Maybe your hospital's a little bit stricter and they say, no, sorry, you'll be less than 5. So 6 a.m., no good. They still can't go home. Wait one more 6 hours. Now it's midnight. So it's midnight. Now they're at 3.25. Now they can leave. So it depends on what your rules are, whether or not to go. But this question wasn't asking at midnight. This question was asking what's it like at 6. So at 6 p.m., we calculated 6.25. Go to our little multiple choice questionnaire there. And there was one option, option B, that matched that answer. So usually for multiple choice, it's a good idea to try to do it on your own. Don't even look at the answers. Or you could take a quick look at the answers and see if there's any really obvious no's, but those were all kind of reasonable looking answers. They all had grams, they all had numbers in them. But for our case here, right, 6 a.m. to 6 p.m., that's 2 half-lives pass, 1 to go to 12, 2nd to go to 6. And then when we do that, we end up with a number here that matches one of the choices. So we went from a 25 grams all the way down to 6 grams over 2 half-lives of time. For that. So that's kind of another way of looking at that problem. But just like the one before, right? As long as you either know what you started with and what you ended with, and they ask for how long it's been in terms of time, or they could say what you started with and how long it's been, and then you got to figure out a mass. There's really only 2 things they can ask about there for those. So those are just kind of some examples of questions like that. And then, do I like this one or not? Yeah, we could do this one. Yeah, so this is just kind of another example here. This was neat on the problem. It was a way of kind of showing, so sometimes you can also do kind of input ones. So I like to do multiple choice ones for class, but you can also do a type in response. So this was a version of that instead. But they're all different kind of variations on that. So this was looking at iodine, and the iodine has a half-life of 8 days. Right, so if you started on day 0 when they first give you this thing, they gave you 40 grams on day 0, and then it's going to take its time breaking down. This one, unlike the other ones that break down every couple hours, this breaks down over courses of days. So it's going to take a little bit longer. But again, you'd want to know how much they have in them. So after 8 days, the first half-life happens. So one half-life happens in 8 days. You go from 40 down to 20. And then you could do it again, 8 and 8 is 16. So you could actually kind of figure out for these ones too. But again, we're always going to give you numbers that are pretty easy to work with. I'll give you another quick second for that one. But for just like here, right, we're always going to try to give you numbers that are pretty easy to divide by 2. So 40 goes to 20, goes to 10, goes to 5. So we'll try to give you answers that are pretty easy to divide. We'll give you half-life numbers that aren't too bad. So 8 and 16 are divisible. We're not going to give you 15 or 20 half-life days. We'll give you ones that are whole numbers that divide easy for those. But that was just kind of another example. But for that one, you saw it wasn't multiple choice. It was kind of a fill-in one. And most people typed in the number there. So, right, so if we went from 8 days to 20, and then another 8 days would be 16, so 20 down to 10. So most people got that one right. But that was just kind of another example. Just like for quizzes and stuff, usually we'll give you multiple choices, but sometimes they're more fill-in, short answers, nothing too long for those. But that's what we can do for any of these half-life type questions. As long as you know how old something is or how long something's been, we can figure out how much radiation is going to be there. And we even use this for anthropology, for other things, for history. So people can actually figure out how old something is, because everybody's a little bit radioactive. Everybody's got a little bit of this carbon-14 inside of you. Every person, every plant, every animal, anything that's made of carbon, which is pretty much everything on Earth, has a tiny bit of radioactive carbon. And after 5,000 years, that carbon starts to break down. So if you die, and they want to figure out, years from now, so if we find some old dinosaur bones, or we find some fossils, or find some old material, and we want to figure out how old it is, we can actually look at how much carbon-14 is in it versus what it should have been, and we can actually figure out how old things are. So we use this for figuring out medically how much radiation you're exposed to, or how much radiation you're going to be getting in you, but we can also use it in a historic context actually to figure out how old something is. We can date how old rocks are, date how old various things are as well. So it has all sorts of different uses using radiation for that. But the other thing people worry about with radiation, right? These things break down at certain rates. Some things break down really quick. Some things break down not so quick. But we're always worried about what happens if you're getting exposed to these. And radiation can cause some issues. Radiation is really high intensity, right? We talked about gamma and X-rays. There are a lot of energy to them. So especially for the gammas versus, the alphas, the betas, the positrons, those have some energy too, but the real thing we're worried about is this gamma radiation. Gamma radiation, X-ray radiation, those are pretty high intensity light. Even UV damage. We know UV can cause damage to cells, because if you ever get really bad sunburns, right, you stay outside the sun too long, that UV damage is causing your cells to die, and that's why you get the sunburn, or why you get the blisters later from that. And if you have too much UV exposure, you also have risk of things like skin cancer or eye damage from staring at the sun. So we already know that UV can cause issues, and gamma and X-rays are even more intense and more energetic than UV. So if UV can cause skin problems, gammas also can. And they do that by actually damaging your DNA. Your DNA has all the information, all the notes for your cells on how to grow, when to stop growing, when to die, when to live, when to pass on and start another cell line from there. And if you mess up that information, the cells may keep growing. They may grow too much, and you can get to cancer. They may instead not grow at all. They may stop growing and die, and that could be bad too, because if all the cells in your skin stop dying, you'd start to lose that layer of protection. Or if all the cells in your gut, where your bacteria and where your digestive system happens, stop growing, you wouldn't be able to eat food, or, well, you'd be able to eat food, but you wouldn't be able to do anything with it after. If all the cells in your blood stopped dividing, you wouldn't have any oxygen-carrying red blood cells in a few days. So those are all really bad things we don't want to happen. We don't want our cells to die in anywhere, especially those important cells and things like blood transport, but all cells are important. We don't want to lose any cells. So we don't want to get exposed to this radiation. It's just some cells are a little bit more exposed or a little bit more prone to being hurt. But any source of radiation can cause this damage to our cells. And that's why people worry about radiation, especially the gamma and the X-ray radiation. And you can get things that cause damage to DNA. They can cause damage to that DNA. In high doses, they actually just kill off the cell entirely, and that's why people with exposure to radiation get sick. But they also, even low doses, can cause mutations and cancer. So even if you didn't get a fatal high dose of radiation, a long low dose of radiation can be bad too, because it won't hurt you right away, but years down the line, you may develop a cancer, and all sorts of different organs are prone to cancer. Pretty much every organ is prone to some type of cancer, whether it's in your bladder, whether it's in your throat, brain, lungs, heart, everywhere can develop different types of cancers. So nowhere is kind of safe from that radiation exposure. Even at low doses can cause a risk. High doses are very bad. High doses are very dangerous, but low doses are dangerous as well. And that's why people try to minimize both their short-term and their long-term exposure to radiation. We have all sorts of laws and regulations about how much you get hit with for that, to kind of protect everybody. So high doses, again, really dangerous. So this would be like if you worked at a nuclear power plant, worked with nuclear medicine, worked at a facility where radiation is used on a daily basis, you could run the risk of a high exposure. Generally, people's day-to-day lives, unless there's some kind of major accident, you're not going to be exposed to large doses of radiation at a given time. But if you do, it causes a lot of problems. It can cause actual physical burns, just like if you get hit with a lot of heat. right? Heat is energy. So is gamma radiation is energy. So it actually can cause burns to your skin. It can cause damage to your eyes, like you get hit with a laser or stared into a really bright light. But it also does damage to all those really fast-growing cells, the cells in your gut, the cells in your blood, cells in your gut and bone marrow. Those are really, really sensitive to bone radiation damage. So all of a sudden you get gastrointestinal issues. You feel like you're really sick. Or the blood producing cells get hurt and you feel like you're really tired because you don't have enough blood to carry oxygen. So these are all not good things for you to happen. But if you also have a more low exposure to radiation, this is something people are more prone to, especially living in areas like New Jersey, where we have high amounts of radon in our basements, people that live in kind of areas with higher amounts of radiation, or people who maybe work at a facility that has some radiation but not a lot. You can get kind of a low daily dose, and that can cause things more like cancer effects, or if you're a person who's pregnant, actually you can have effects on the baby too. The baby can develop some issues before they're born there. But these are things we want to avoid. So because of that, we try to avoid both of these. We don't want you hit with a lot of radiation at once or a lot at a little time. We make rules and regulations to kind of protect you from that. But you know, for radiation, it does look like a burn in some cases. So if you get exposed to radiation, depending on how big or how small it was, this was a person who was working on an X-ray machine. X-ray machines normally have a safety thing to keep the X-rays kind of from coming out. But in this case, the safety thing was broken and they had their hand where the shutter was. And what's kind of interesting here is you can see the rest of their hand is fine. It's only where the X-rays hit that the damage occurred. So radiation, high doses, depending on whether it's whole body versus localized, can have different effects. But in this case here, it was relatively localized, which was good for them. They only had some minor damage here. They were able to get treated for that, versus if it was a larger dosage, it would have been much worse. Same thing here, you can see very clearly where they were exposed and not exposed. And this was the same thing with an X-ray issue, but they happened to be holding something halfway across their hand, and half of their hand was saved because this half of the hand was on one side of the plate and this side wasn't, and this side got hit with the X-rays, but that side, or the gamma rays, but that side didn't. So shielding is really important. If you can have other things to protect you, you can actually be really good. But you have to be careful with working with these things. And these were faulty equipment, so that was some issues with that, making sure equipment is made the right way, protecting people from that. But we want to avoid high doses of radiation. So high doses of radiation, like these cases here, were relatively high dose, but short area and short exposure, just your hands are relatively okay. You can get, you know, if you ever had burns on your hands from handling hot water or things like that, from cooking, you know, it hurts, but it's not the worst, versus if you get a burn to other parts of your body, it takes much longer to recover. Your hands are pretty good about recovering because they're far away from your core. But if you get core damage from radiation, so if that beam, instead of hitting your hands, hit you in the chest, it would be a lot worse. And that's where you actually can have some really bad problems depending on how much radiation you get hit with in a short amount of time. Really short amounts of time with low dosage, 25. So these are arbitrary, these are units that are somewhat arbitrary. We can't really test this very well. So you can't just get a bunch of volunteers and say, hey, we're going to hit you with 100 units of radiation and we're going to see how you do. That's not a very good, very ethical thing to do. But there have been various disasters like these examples here. And based on the disasters and calculations, we kind of figured out, based on some accidents and things that have happened, what kind of your safe levels are. And for really short doses of really high radiation across your whole body, less than this 25 unit, but it could be more. Some people could take up to 40, 50, they'd be fine. Some people may start to feel these effects after only 10. But generally kind of this this dose here, nothing bad. And then as you get increased with higher and higher amounts of radiation, you see kind of increasing effects. And it has to do with the cells that are affected. The cells that are most worried about or most susceptible are the cells in your stomach and the cells in your blood cells at first, and then the other cells after get more damaged. But because you start to lose your blood cells, the blood cells, red blood cells carry oxygen, you feel tired. And that gets just worse and worse with higher amounts of radiation. Because your stomach is also really sensitive to radiation, you feel like you got food poisoning. You felt like you ate some bad food. And it gets worse and worse as it gets along. You also can actually have damage to your white blood cell count. White blood cells protect you from infection. So high doses actually can kill you not from the radiation, but a random infection or a random cut that causes bleeding problems, because also your platelet count, your ability to form clots can be hurt as well. And even these doses, right? Low doses of radiation or medium doses of radiation, 3 months to recover, as long as you don't get hurt by another infection, as long as you don't get hurt by bleeding out from other issues. And then really high doses are fatal relatively quickly or extremely quickly, again, depending on how high. But even for these other doses, 2 to 6 weeks where you may or may not make it, and then 6 months where you're going to recover from. So even one very short high burst radiation, maybe a couple of seconds of exposure, takes you 6 months to recover. So we don't want this to happen anyway. We want to avoid people getting the burns. Those are bad enough. The higher doses are even worse. So we have warning symbols for that, right? We have little kind of symbols that say, hey, this is dangerous. This one's not the most, notable symbol. It's the one that's used. Doesn't really mean something. What does it mean? It's like some kind of fan or something. So there's 2 radiation symbols. There's another one that's used because there have been issues in the past. We'll talk about that next time instead, but kind of modernized symbol. So if you're ever working in a hospital, you'll probably see this one. If you ever work for an X-ray machine, technician, things like that, you may see this one, and this is the one you're not supposed to see. So this is the one that's hidden inside the X-ray machine. So if you're an X-ray technician, you open up the panel, and then you get to this thing. And that's kind of more of a, hey, you're not supposed to be handling this unless you know what you're doing, because if you're not sure what you're doing, that's where you risk things like this or other disasters we've had. We've actually had a couple of major disasters with bad sources or bad X-ray machines that were scrapped at scrap yards or sent away to be junked at a junkyard. And the people there didn't know what it was because there was no warning. And they accidentally got killed because they were working with something that shouldn't have been sent to their junkyard in the first place. Some of these cases were really bad, like the one in Brazil, where a small sample the size of, not even something about a quarter the size of this, filled up 2 Olympic-sized pools with waste, because the waste is so concentrated, so dangerous, that it got out into the open and it spread all over the countryside because it's very fine powder. So that was really bad for that whole area. It was a pretty bad case. 8 people got killed in that accident because it was sent to the wrong type of facility to be junked. So it was sent to a regular scrap metal plant instead of a proper place that knows how to handle this, that was warned about it. No one knew that it was dangerous. There was no warnings. There was no things, because unfortunately radioactive materials, they don't glow, in TV shows, they're that bright glowing green color. No, they don't really look like anything. They look like rocks. They look like regular material. So unless there's a warning on it, you don't even know that you're handling with it until a couple of days later when your skin gets really hurt or you're feeling really sick. And that's what makes radiation so dangerous, but also why people are afraid of it because it's invisible. You can't see it. You don't have, just like carbon monoxide can kill you without knowing it, the radiation, you're going to just suddenly start to feel sick and you don't quite know why. It's not like you're getting, you don't hear the sound of a beam, you don't see something glowing or giving off a weird color. So if you do work for a hospital or a facility that does nuclear medicine, just be careful what you're working with. Make sure they tell you what you're working with. They'll give you protocols, how to shield yourself, how to protect yourself. Make sure you follow the rules. Keep track. Ask questions if you don't know, because we'll make sure everybody's safe for that. So we'll talk about how to actually protect you from exposure next time. And again, this is usually only for really large sources of radiation. Most of the facilities, if you're just handling with a patient, you're giving them some medicine that's radioactive, that's okay. But if you're the one who's actually dishing out all the medicine for the day, then you're near larger sources. Or if you're the one who's going to be operating that X-ray machine or kind of working with those units or working on that floor with the chemotherapy, then you may be exposed to a little bit larger doses. But there's ways to keep you safe, and we'll go over those on Tuesday next time, how to actually keep people safe. And we saw some of those in lab too, how to kind of keep everyone kind of shielded there. But any questions about stuff today, or kind of covering a lot at once?